Hi, this is Dr. Matsuko with a short micro lecture on particle in a box, sometimes also called one-dimensional infinite potential well. Infinite potential well. That's the more technical name. I prefer to call it particle in a box. All right, so we are going to picture or visualize an electron stuck in a box. Stuck in some kind of potential box, and it's kind of like the size of an atom or something. So this is basically we're imagining an electron stuck in a square one-dimensional atom, and then from there we're going to apply Schrodinger's equation, see what kind of solutions we have, and that will actually help us to start thinking about what happens to an electron in a real atom, which is actually spherical in 3D and not infinite, it's finite, right? But there's a lot of lessons that we can learn from putting an electron in this one-dimensional infinite box, right? And so the electrostatic potential that's keeping your electron in your box due to the positive protons is similar in idea to gravitational potential. So that's what this picture is here. There's some kind of potential well that your roller coaster can go up and down, but there's some max height that it can go to. And this picture on the left is actually a finite well rather than an infinite, whereas I'm going to focus on an infinite one. One interesting thing is that for electrons, we've been talking about wave functions, right? So if you have a particle that's stuck in a box, how can it be a wave? It is a standing wave. And if you need to review that, we covered that last semester talking about simple harmonic motion and for strings that are vibrating. We did this in lab as well, so that's a standing wave. All right. And so, there we go. We're going to apply a Schrodinger equation. All right, so actually, we're not going to apply it. The textbook goes through the whole derivation for this, and there are actually multiple videos online that go through the derivation of this. I'm just going to jump to the solutions. But what you would do is that this V here is your potential, and you would apply this infinite potential well in V, right? And then we have all of these C's, those are our wave functions. Wave function, which we've covered in previous videos. And then there's all these other constants and stuff. One thing that's going to be important is energy, right? We're going to, the solutions tell us not only the shape of the wave function, but also the energy of the electrons, or the allowed energy of the electrons. Right, what are the physically possible states? What shape of C is allowed, and what energy are allowed? Are physically allowed, because there are some of them that are not allowed. So we're going to jump to our solutions here. And so this one slide holds a lot of the most important information. It's the final solutions for this problem. All right, if we start from the left, there's the energies. I do put eigen here. You don't really have to worry about the eigen. I don't think that shows up in the textbook. You'll talk about eigenfunctions and eigenvalues in Diffie Q, maybe, if you so it's a further math class. It's one way to solve this problem, but again, I'm not going to actually do this derivation, right? But so our energies for a 1D box, we find that one of the important things is that energy is quantized, and so you have these n, which is going to be your level. Right, and so you have your ground level, which is going to be n equals 1, and then you have an n equals 2, and you have an n equals 3, and so on, and so on, and so on. And we find that the energy depends on n squared. So for higher ends, for higher levels, the energy grows with a square. So your lowest energy is going to be the ground state, and then your higher energies are squares of that, right? 2 squared, 3 squared. And then E1 equals h squared over 8m L squared, where L is the size of the box, m is the mass of the particle, and h is Planck's constant. For the states, the actual wave functions themselves, we find that they actually are sines, or they're sinusoidal in shape, right? They have a magnitude of root 2 over L, and then we have n shows up inside the sine term, right? And that actually changes the wavelength, right? So for the n equals 1, we have at the wavelength equals 2 times L. For n equals 2, we have at the wavelength equals L. For n equals 3, the wavelength equals 3 over 2L, and again, it keeps going. All right, so the amplitude is going to be the same for all of them, but they have decreasing wavelength. As you go higher, as you increase n, your wavelength is going to decrease. But it always has to fit in here. You always have to have 0 at the boundaries. Your wave function, which is directly related to your probability, has to be 0 at the walls, which basically means there's no electron inside an infinite wall. Right, and that's directly related to probability density, right? Probability density is the wave function squared, right? And so that's just how you get all of these things. You just square them, and that's the equation below. So you want to be able to calculate, make sure you can calculate psi, that should have a little n there, and the shape of the wave function, how it depends on n, and also you'll definitely be calculating energy and how it depends on n and L, and also probably mass will show up as well. Right? This is kind of an aside, but I just think it's interesting that this equation, equation is also an approximation for quantum dots or nanoparticles, right? So my PhD work, part of it was on making nanoparticles, which meant that this diameter of your sphere or the size of your particle was somewhere on the order of a nanometer, and so you could actually count how many atoms are on here. There were thousands of atoms, and I had friends that would take pictures of these, and so you actually can trap an electron inside this nanoparticle rather than inside an atom, and the equations for this follow something similar, right? You might notice, you'll be asked this on the homework as well, right? This L, the size of the box, how the energy of the states relate to L, the size of the box, right? So if L is bigger, right, then we find that our energies go down. Energy is less, right? And so it follows the same trend. This has been proven for nanoparticles. It's been proven for organic molecules. And so there's a lot of experimental evidence that basically you can follow the same trend. So even though this equation is just for a one-dimensional infinite box, it still gives us a close approximation to what's actually happening in real life. Right? And so there's some nice pictures of quantum dots. And again, this is some evidence, right, that as L increases, we find that energy is decreasing. Whoops. Again, we have energy equals hc over lambda. That was last lecture. Right, and you can get some nice pictures. I collaborated with Bundy. All right, so let's do a couple of practice questions. All right, so what's the energy of the n equals 3 electronic level in a 1D box I didn't put infinite, but anyways, with a width of 2.5 nanometers. So again, this is basically plugging in. What's the energy? We get h squared over 8 m. This is mass of an electron, right? We're told electron. And then L, 2.5 times 10 to the minus 9. And then n squared is 3 squared. Right? So E will equal, and then we can decide whether we want to do EV or joules. Right? We can totally choose what we want. I'm going to put this in electron volts because I prefer electron volts, but you can just choose what you want. All right, so our H, we have 4.1 times 10 to the minus 15 squared divided by 8 times 9.1 times 10 to the minus 31 times 2.5 times 10 to the minus 9, and then times 3 squared, and that one I chose electron volts. Another direct application of this is excitation and emission, right? And basically if you have an electron that's in the n equals 1 state, it can actually jump up to the n equals 4 state, and there's some delta E in there, right? And so that delta E is just energy high minus energy low, and usually we relate that to energy of a photon, right? And this is referred to as absorption, right? That an electron or any particle can jump from, can gain a delta E by absorbing by absorbing a photon. Right, and you can also go the other way around. You have a delta E if it's going down, and it can go down in different ways. What's going on? You can it's so-called de-excite. I commonly call it fall down. But anyways, it's going to de-excite, and when it de-excites, this delta E, it gives off again in a photon, and so that's called emission, and that gives off really nice light, and that's how LEDs work and lots of other colorful stuff. So I have one problem on that, a very similar problem, right? So what is the energy of the photon emitted when an electron de-excites from n equals 3 to n equals 2 with a width L, right? So your energy of your photon is just going to equal that delta E, and that's going to be the energy of the high, which is n equals 3, minus the energy of the low, which is n equals 2, right? The smaller number has the smaller energy, right? And so we get E photon, and I'm going to actually bunch up the constants over here. 8 ME 2.5 times 10 to the minus 9, and then I'm going to, over here we have the n squared, and so we have 3 squared minus 2 squared, and that way I don't have to plug in all these constants a lot. And so your energy of your photon equals, right? So that is all of our application and some practice problems for a particle in a box.